Mastering Principal Component Analysis. Principal component analysis succeeds only when it juggles dimensionality reduction, information preservation, and simplicity in data representation. Who is responsible for ensuring that the primary goal of principal component analysis in operational excellence, which is to identify the most relevant variables that capture the greatest variability in a dataset, is achieved through its ability to reduce dimensionality, minimize information loss, and provide a simplified representation of complex data. In the realm of principal component analysis, PCA, for operational excellence, the primary goal is to identify the most relevant variables that capture the greatest variability in a dataset. This is achieved through PCA's ability to reduce dimensionality, minimize information loss, and provide a simplified representation of complex data. The responsibility for ensuring the achievement of this primary goal lies with the data analyst or scientist responsible for conducting the PCA. This individual must possess a deep understanding of the underlying principles and concepts of PCA, as well as the context and requirements of the specific operational excellence project. To begin with, the data analyst must carefully select the dataset to be analyzed, ensuring that it is relevant to the operational excellence project and contains the necessary variability to facilitate meaningful insights. Next, the analyst must pre-process the data by cleaning, normalizing, and transforming it into a suitable format for PCA. Once the data is prepared, the analyst must choose an appropriate PCA algorithm and determine the optimal number of principal components to retain. This decision is critical, as retaining too few components may result in loss of valuable information, while retaining too many may lead to overfitting and decreased interpretability. Upon selecting the optimal number of components, the analyst must then assess the results, focusing on the proportion of variance explained by each component, the component loadings, and the corresponding eigenvectors. These metrics provide valuable insights into the underlying structure of the data and enable the identification of the most relevant variables that capture the greatest variability. Furthermore, the analyst must also consider the importance of dimensionality reduction, information retention, and simplification of complex data. PCA's ability to reduce dimensionality enables the identification of patterns and relationships that may have been obscured by the original high-dimensional data. This, in turn, facilitates more effective decision-making and process optimization within the operational excellence project. In addition to these technical aspects, the data analyst must also consider the practical implications of PCA results on operational excellence. This includes communicating the insights and recommendations to stakeholders, developing actionable strategies for process improvement, and ensuring that the results align with business objectives and key performance indicators, KPIs. Ultimately, the data analyst is responsible for ensuring that the primary goal of PCA in operational excellence is achieved by carefully navigating the nuances of data pre-processing, algorithm selection, component retention, and results interpretation. By doing so, the analyst can unlock the full potential of PCA, providing valuable insights that drive operational excellence and business success.